Previously, we talked about Pascal's triangle, this construction that involves our k combinations, and and the way we came up with Pascal's triangle is we enumerated over values of k and n choose k, and we noticed a property that allowed us to compute successive values in Pascal's triangle called Pascal's formula, and we proved that that formula can indeed be used to compute successive row entries in the triangle. So just for context, I drew the triangle here, not left aligned. It'll be a helpful aid for discussion here. So we're going to talk about some properties. By no means is this a complete list. We're going to talk about some properties of Pascal's triangle. And if you're curious more about some of these more delicate details, let me know. Let me know. Let's talk about some properties of Pascal's triangle. So the first thing I want to point out is I alluded to this idea that there's a lot of combinatorial properties that exist in Pascal's triangle. That shouldn't be very much of a surprise so far. You may be staring at this and you might see some interesting things already. But I'm going to start at some simpler, more direct relationships, then we'll kind of dig in a little further. So I'll also derive and convince you that one of these actually isn't nothing to do with black magic or anything like that. It makes complete sense if you use Pascal's formula. So we're going to highlight some. So highlighting a few properties Pascal's triangle has many. I know it sounds a little funny. I'm just getting really excited here. So highlighting a few properties, Pascal's triangle has many. So for example, many number sequences appear in it. So just as an example, so I'm going to give you these examples, and then we're going to see where they are in the triangle, okay? So while I'm telling you about the number sequences, see if you could find them in this triangle. They actually can appear in several different ways. I'll just highlight one way they can. So they can appear in many different ways. This has to do with several factors, such as the symmetry along the triangle when you read it from like this direction or from this direction, and there's a few other ways as well. So, for example, you can consider the positive integers. So 1, 2, 3, 4, 5. So where are the positive integers in here? So there's at least one way you could find them, right? There's at least one way you can find them. So you might see them right here. Right there. Or you might see them like this too. There's your positive integers right there. Let's consider another example. Let's consider the triangular numbers. Some people call them just triangle numbers. So if you've never heard of the triangle or triangular numbers, this is just each term is the sum of the numbers up to that term. So for example, the first triangular number is 1. The next one is 3 because this is 1 plus 2. The next one would be 1 plus 2 plus 3, which is 6. The next term would be 1 plus 2 plus 3 plus 4. So just, you got to look at it like it's the next level above this in terms of adding the terms. What's 1 plus 2 plus 3 plus 4? That's 10, right? Okay. What's for the fifth term? It should be 1 plus 2 plus 3 plus 4 plus 5. That is 15 because it's just simply this plus the next term. then you can keep doing this forever. So the reason why they call triangular numbers, I'm not going to focus so much about this here. So you can imagine I write out a triangle like this successively like this and ask how many of these balls or dots exist for each successive triangle based on how many rows I include in the triangle. So notice this has 3, third one has 6, fourth one has how many? 10. And you keep this process going. So where are the triangular numbers? Let's keep it to the same orientation I did before. It's directly below the positive integers. Right here. So there's your triangle or triangular numbers. Okay. I'll even throw another number sequence in here. There's even more. I want to stress this is not a complete list by any means. So here's another example. So there's what we call tetrahedral numbers. And it has a very similar relationship to the above two sequences. So this one is where you take each term of the triangular numbers and you successively add the first I of them. So the first term is 1. The next term would be the sum of the first 2 triangular numbers, 4. The next term, the third term, would be the sum of the first 3 triangular numbers. So in this case, it should be 10. Then the next term of the tetrahedral numbers should be the first 4 triangular numbers summed up. So notice that this will be 1 plus 3, that's 4, plus 6, that's 10, plus 10, that's 20. And you can do the next one, it's 35. Where are those? Well, you see 1, 4, 10, and then we'll go 20 and keeps going down like this. So there's your tetrahedral numbers right there. You might guess quite quickly that this has something to do a little bit with geometry, but I'm not going to highlight that right here. So there's your tetrahedral numbers right there. So there's a whole bunch of number sequences that pop up in this thing. These by no means are the only ones. But you might look at this and say, Dan, why would the triangular numbers pop up in here? Is this some spooky stuff that I should watch out for? Is this some black magic? So I assure you this isn't some sort of like splay tree or something. That's a joke, by the way, just to be clear. It's actually because we can actually show that this is indeed going to be what happens in Pascal's triangle. So why don't we try to derive a reason for why this would be the case? So I want you to look carefully at where the triangle numbers begin and why would they start appearing there. So why do the triangle or triangular numbers why do they appear in here? So just for context, if you're wondering how you determine the ith term of the triangular numbers, it would have a form that looks like this. You might recognize this as the closed form for the arithmetic series. So it's going to have a form that looks like that. So why would it pop up in here? So why does it appear in there? So notice, so I want you to look carefully at that triangle. Remember, as we do this, so each one of these successively is going to end up being different values of k. So this is when k is 1, this is k is 2, this is when, this is k is 0, that's k is 1, k is 2. So notice this is when k would be 2. If you're not convinced by this, please look back at our table we computed when we were deriving Pascal's triangle. So this would be the row for when n is equal to what? Well, let me lay out the condition. So please, let's take a look. So notice every position, a triangular number appears. I might call them just triangle numbers for brief if it makes it a little bit too much. Notice every position a triangular number appears is whenever k is equal to what? So this is k is 0, k is 1, k is 2. Whenever k is equal to 2. Specifically, this happens when if n plus 1 is greater or equal to 2. That I get each successive triangle number from there. So it's going to make it a little easier for us to work with if we notice that we can get each successive one if this is satisfied. So if you aren't seeing it right away, it's just the same as me writing n is greater or equal to 1. So if I subtract 1 for both of these. This is just to make it so it's a little easier for me to compute each successive triangle number. So you're going to see that I'm going to find some way of getting each successive triangle number from a previous one in some way. Well, what does that mean? So each row, I should say successive row, corresponds to a value for n plus 1. So let us compute n plus 1, choose 2, because that's what k is. Each successive triangle number will appear the one next to it, right? So I want to do something with the triangle to know each successive one. So let's do this. Well, we can use Pascal's formula. Well, by Pascal's formula, well, let's see what happens. So I have n plus 1, choose 2. Pascal's formula tells us this is n choose 1 plus n choose 2, right? That's what Pascal's formula would tell us this is. Well, n choose 1 is easy. That's just n, right? And then n choose 2 is n factorial over 2 factorial times n minus 2 factorial, right? Well, just to make this a little easier to work with, I'm just going to write this out a little bit more carefully. Well, this is n plus n times n minus 1 times n minus 2 factorial, right? 2 factorial n minus 2 factorial. Well, the n minus 2 factorials cancel each other out there, and I end up with something that will look like n plus n times n minus 1 over 2. I'm just going to bring this all under a common fraction or common denominator. So that means I'm going to have 2 n's over 2, because that's equal to n. So I'll have 2n plus n times n minus 1 all over 2. Let's expand the second term. This is just 2n plus n squared minus n over 2. Well, what's that? Well, I have 2n minus n, so it's just n, right? Well, that's just, well, it's not that we don't have a 2n anymore. We just have n, right? So it's n squared plus n divided by 2. But what's this? What's this? Let me factor it so it looks a little nicer like that thing I have over there. Well, it's n times n plus 1 over 2. Boom. There's the general, that's the general term for the triangle numbers, right? And that it's not a coincidence. It appears in Pascal's triangle. It's not, no black magic here. It's not just the coincidence. It just appears in that construction for this good reason. It always will have that form. So Interesting stuff. So different number sequences can appear directly in the triangle. That's the first thing. The next thing is that you can go even further. There's sometimes properties where the triangle actually has hiding in it through successive operations, such as adding over parts of the triangle, different things. It's not black magic. Right, my little friend? It's not black magic. I'm not getting any answers, okay? So, they're not black magic. But you could actually find other reasons why other things appear as well. So let me show you another peculiar one. But it is surprisingly neat. So watch this. So what I'm going to do next is I'm going to show you that there's these shallow diagonals that exist in Pascal's triangle. Now, if you don't like the way I'm doing this with just this triangle, just look at the diagonals in our table when we computed Pascal's triangle previously. So let me do this carefully. It requires some artistry to get this right. So anyways, so I'm going to do some shallow diagonals. So I want you to notice something. It's interesting. It's happening. It's those two. Yeah, we're doing good. We're doing good so far. Sorry, this takes a lot of patience. It's just drawing lines. Okay. I want you to notice something. Add the numbers that appear on each one of the red lines. So each one I crossed over. So I have 1, then I have a 1, right? 1, 1. This has 2. This one has 3. If I add up, 1 plus 2 is 3. 1 plus 3 plus 1, that is 5, right? 1 plus 4 plus 3, that is 8. And you can keep making shallow diagonals like this. Does anybody recognize that number sequence that I have written up there? And keep in mind, this keeps going on. Like, you keep this pattern going. Does anybody recognize that number sequence? What is that number sequence? So others appear too. So just as an example, you might know about the Fibonacci numbers. So the Fibonacci numbers are defined as follows. So I'm just going to define it like this. Fib of n is going to be equal to it's the previous term plus the term just before that one, 2. So fib of n minus 1 plus fib of n minus 2. Or suppose that you define fib of 1 to be equal to 1 and fib of 2 to be equal to 1. So if you notice this, it means that each term is the sum of the 2 previous terms. So I have 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8. And you can keep going this. So summing the shallow diagonals produces the Fibonacci sequence. So that's interesting, right? Now, there is a good reason for that. You can actually prove, if you formalize what these shallow diagonals are carefully, you could prove using mathematical induction this is in fact the case. Now, Let me show you another property. So that's one way you can add things in Pascal's triangle. You can also find some other ones as well. So I want to show you another way you can add some across the table. So I'm going to use a blue marker. I'm going to draw in some more lines. I'm really ruining this picture. But the point I'm getting at is that there's a lot of things going on with this triangle. So I'm going to put some lines through each row. So what does this row add up to? If I look at the numbers in that row, it's 1. How much does this add up to? 2. How much does this add up to? 1 plus 2 plus 1. So 1 plus 2 plus 1, that's 4. 1 plus 3 is 4. 3 plus 1 is 4, so this is 8. 1 plus 4, that's 5. 4 plus 1, that's 5. 6 plus 10 is 16. And you can do the same thing here. We got 20. We got 30 and 32. What's going on these rows? What are those? What are those? What's happening on the rows if I sum up across the rows? So each sum of a row equals a power of 2. So notice that 1 is equal to 2 to the power 0. 2 is equal to 2 to the power 1. 4 is 2 squared. 8 is 2 cubed. 16 is 2 to the power 4. And 32 is 2 to the power 5. And you might ask, Dan, why is that true? Well, there's something rather interesting if you think about it. This is actually just a summing across all values of k and choose k, right? Because each row is a value of n. And the values here, these are all the ones where k is less than or equal to n. And whatever that is, the claim here is that that's equal to a power of 2. Now, I'm not going to prove that here, but we're going to actually implicitly prove this when we study something called the Binomial Theorem. So the Binomial Theorem actually gives us the answer to why this happens. So the Binomial Theorem actually gives us the answer of why the second one occurs.